Alright, this is about Maxwell's equation. Maxwell's equations are the basic laws of, which governed the property and the characteristics of the electric and magnetism. So these laws are very important because with the help of these law, Maxwell could explain about, the nature and the property of electromagnetic wave. Okay, so these equations, they consist of four equations. And these four equations are known as Maxwell's equation. The first equation that Maxwell works is Gauss's law in electrostatic. If you remember, Gauss's law in electrostatic says that the electric flux which is passing through any closed surface is equals to 1 upon epsilon naught times the charge enclosed by the surface. Okay, so that means phi E, which is the electric flux, is equals to charge upon epsilon naught. Okay, but this phi E we have seen right before. If you go back to the video right in the chapter of electrostatic, you will find that this phi E is written as E dot ds. So this E dot ds is equals to Q upon epsilon naught. So what is the importance of this equation? Here we have a charge. When there is a charge, there is what? An electric field. So a single charge always produces an electric field. Okay. Or I can say, when there is an electric field, automatically there should be a charge because electric field cannot exist without a charge. Alright. So that is the meaning of this equation. Number 2. Gauss's law in magnetism. Gauss's law in magnetism says that the total magnetic flux over a closed surface is equals to 0. Or I can say B dot ds is equals to 0. It is just like E dot ds only, which is the electric flux, but here instead of E I replace by B. So when you replace by B, it means the magnetic flux. So magnetic flux over the surface is equals to 0. It means that if this is a magnet, with this is the north pole and this is the south pole. If I draw a closed surface over this magnet, then if this is the magnetic field lines coming from the north pole, okay, because magnetic field lines are always generated from north pole, and these line right, they'll go to the south pole in this way, and inside they will be going from south to north like this. So looking at this line right, we can say that they form a closed path. So any line which form a closed path, okay, will not produce any flux over the surface. So that means that, okay, are you getting my point? Because if this is the line which is going perpendicular, right, or I can say which is passing through this surface, then this is the line which is coming into the surface. So one line is going out, one line is coming in, so they will cancel out each other. So that is why we get the magnetic flux over the closed surface is 0. Or in other words, I can say that a magnet always exists in pair. We have north pole and south pole. We cannot isolate or we cannot separate the two poles of a magnet. So that is the meaning of this equation. Okay. Number 3. Faraday's laws of electromagnetic induction. If you remember, in Faraday's law, we say that the EMF which is induced in the coil is equals to d phi upon dt. And this phi here is different from this phi. Okay, I have wrong. So sorry. So this phi b means the magnetic flux. And this EMF, it is the same as the line integrals of the magnetic field. Okay. Now, for phi b, I will write it as, because we know phi, okay, is equals to phi b is equals to b times a, magnetic field times area. So b times a. All right. So here what we see, d dt of b. So it means the magnetic field is changing with time. So when the magnetic field is changing with time, then you will get what? Electric field. Okay. So this is the meaning of Faraday's laws of electromagnetic induction. And the fourth equations of Maxwell is the modified Ampere's law. And this modified Ampere's law, it is equals to this much. The line integral of the magnetic field around any closed loop is equals to mu naught times the conduction current plus mu naught epsilon naught d phi a upon dt. Okay, where these things here stands for what? The displacement current. I hope you still remember. So similarly, this equation, it can be further written like this. Now instead of phi e mean electric flux. So for electric flux, I'll write it as EA. Magnetic flux is BA, so electric flux is EA. Okay, so here E is changing with time. So when the electric field is changing with time, then we get a magnetic field. Previously in equation number 3 in Faraday's law, a changing magnetic field produces an electric field. But now a changing electric field produces a magnetic field. So these last four equations, the last two equations, they are very important, which make to the conclusions of Faraday's laws about electromagnetic wave. So based on these two equations, Faraday's find that a change of either field will produce the other field, which means a change of electric field will produce a magnetic field. And if you change the magnetic field, you will get an electric field. Okay. And Maxwell further showed that the variations of electric and magnetic fields occur mutually perpendicular to the direction and have a wave-like properties. He thus led to the idea that a wave of electric and magnetic field, both varying with time and space, they should exist, and such wave is known as electromagnetic wave. So what is an electromagnetic wave? An electromagnetic wave, it is a wave which is a varying electric and magnetic field and which are traveling in a medium perpendicular to each other and as well as to the directions of propagations of this wave. So that is an electromagnetic wave. Alright, so that is how I told you from the beginning that with the help of Maxwell's equation, right, we can determine, or we can determine about the characteristics and the nature of the electromagnetic wave. So now we have just defined electromagnetic wave as a wave which consists of varying electric and magnetic field. Alright, so in the next video we will see how do this electromagnetic wave can be represented.